Hello all. Today in this video we are going to see about carbon NMR, okay, C-13 NMR spectroscopy. So first of all, what are the types of, isotopes of carbon available? C12, C13, C14, right? Among these, carbon 12 is present in abundance, okay? Natural abundance is very high. It will be around 98.9%, okay? 98.9% of the carbon isotope will be C12 isotope. Right. Next, if you see about C13, it is only 1.1%. Okay. Abundance will be only 1.1%. If you take this C14, it is radioactive isotope, right? It is used to find out the age of the particular species, okay, specimens. So, what we want to see here, which carbon isotope will be NMR active. It is very simple. In the first video I have told you the rule, right? What's the rule? Both atomic number and mass number should not be even, okay? If both the atomic number and mass number are even, then that particular nucleus will be NMR inactive, okay? NMR inactive. I value will be 0 for that species, okay? See here in this case, 6, atomic number is 6, it is even, and similarly mass number is also even, right? Hence this will be NMR inactive. It will have an I value 0, okay? Similarly in 6 carbon 14 also I value will be 0 and it will be NMR inactive nuclei. Actually it is radioactive, it is not present, okay? So this is the only isotope of carbon that is NMR active, right? This is the only isotope of carbon that is NMR active. It will have a value of I is equal to half. Okay, I is equal to half. Proton NMR also have an I value of half, right? Proton also have an I value of half. And similarly, 13 carbon is also having I value half. Okay. These are the similarities between the carbon and proton. Okay. Suppose you are having a sample, right? Suppose you are having a sample. For example, CH3, CH2, Cl, okay, ethyl chloride. In this case, see, this can become, if this is carbon 13, then definitely this will be carbon 12. Why? Because it is a dilute nuclei, right? C13 is a dilute nuclei. I told you the abundance is only 1.1%, right? 1.1%. It is negligible amount. So, if you have C13 here, definitely there won't be C13 here, right? What do you mean by dilute nuclei and concentrated nuclei means? Concentrated nuclei means the species will be rich, okay? Abundance will be greater. But dilute nuclei means it will have very low abundance, very less abundance, right? I told you that 98.9% is carbon 12 and only 1.1% is carbon 13, right? So there is no but it is NMR inactive. Hence, the possibility of having C13 is very less, okay? Very less. So if this is C13, obviously this won't be C13, it will be C12, right? Now we are going to see the chemical shift values, okay? Chemical shift values for C13. If you have watched the previous video, then it will be very easy. So if you haven't watched, kindly watch the proton NMR video first. Because if you watch that video, this concept is very simple, okay? See here, these are all the chemical shift values for C13. So you just take the screenshot of these values. It will be really useful when you solve the problems, okay? So, this is the sp3 hybridized carbon has a value of 10 to 40 ppm, okay, 10 to 40 ppm. When it doesn't attach with electronegative group, only sp3 carbon is alone present, no electronegative group is attached with the sp3 carbon, okay? In that case, it will have a value of 10 to 40 ppm, okay? But if suppose your group is attached with sp3 carbon is attached with an electronegative group, in that case, see here, the value will be high, 40 to 80 ppm. Because I have told you the concept, if an electronegative group is present, what will happen? It will tend to pull the electron towards itself, okay? Suppose here you are having CH2Cl, okay? CH3Cl is present. In this case, the electron will be pulled towards, okay, electron will be moved towards the chlorine atom because it is an electron withdrawing group. In this case, electron density around the hydrogen will be less, okay, electron density around the hydrogen will be less. It is de-shielded. Whenever you are having a de-shielded group, it will have higher chemical shift value, okay. As a result, if your sp3 hybridized carbon is attached with an electronegative group, then it will have a value of 40 to 80. Both are sp3 hybridized carbon, okay. What's the difference? Here there is no electronegative group. Here there is an electronegative group. So if an electronegative group is present, then the chemical value shift, okay, chemical shift value increases, right? Now see here, sp2 hybridized carbon. See, these two are for sp3 hybridized carbon. Only sp3 10 to 40. If you are having an electronegative group, then it is 40 to 80 ppm, okay, 40 to 80 ppm. See, in this case it is sp2 carbon, okay, sp2 carbon. Obviously this will have a greater value, right, greater ppm. It is 100 to 150 ppm, okay, 100 to 150 ppm. And in sp case it is 80 to 150. So what are all the values for those? See here, the sp2 4 to 5 is for hydrogen, and in sp 2 to 3 is the value for hydrogen, okay, proton NMR. These are all for C-13 NMR. And see here, for carbonyl group, there it was around 8 to 10 for aldehyde and ketone, and above 10, okay, above 10 for acids, like 11, 12, okay. Those are all for acids in proton NMR. And in C-13 NMR, this carbonyl group aldehyde and ketone will have a value of 150 to 220 ppm, okay. 180 to 220, okay. 180 to 220 ppm will be there for carbonyl group. For aldehyde and ketone, 180 to 200 ppm, right? These are all the values for C-13. So you just take the screenshot of these, okay. Then we are going to find out the number of signals for carbon, okay. Find out the number of signals for carbon. So if you have practiced for proton NMR, then this will be really easy, okay, really easy. See here, I will give you some compounds. You just find out how many signals are possible for those compounds, okay. Okay, can you find out the number of signals for these compounds? I have given you 9 compounds, okay, 9 compounds. So for these you have to find out the number of signals, okay. You just try it on your own, and after that you check it with our answer, okay. See here, in the first case, actually we have to find out the number of signals. Number of signals means type of carbon, right, types of carbons, that is carbons in different chemical environment, okay. See here, in this case, this is methyl, okay, this is methyl. First of all, do we have plane of symmetry? No, we don't have plane of symmetry, okay, fine. So everything will be different. This methyl proton is A, okay. Then this CO has CH3 and OCH to this side. So it is different, right, from this. It is a methyl group, but this is a carbonyl group, right? This is different. So it is B type of proton, okay. Next, the next CH2. The next CH2 group is attached to oxygen. So it is different. Hence, this is C, okay. And this is D. You can't say these two methyl groups are same because you don't have plane of symmetry and you don't have same groups on both the sides, right? This CH3 is attached to CH2, but here the CH3 is attached to CO, right? These are different, entirely different. Hence, here you will get 4 signals, okay? 4 signals. Now, see this case, okay, we will solve it later, okay. In this case, there is a possibility of plane of symmetry, right? You can draw plane of symmetry here, right? You can draw it. So, after drawing plane of symmetry, what will you do? You can just calculate the number of signals on one side alone, right? So, this is A type of carbon, okay. This is B, this is C, and this is D. Because see here, from this methyl group, it is quite distant one. It is far away and this is far away. This carbon is attached this methyl group is attached to this carbon, right? So this carbon is different from this carbon, and this carbon is closer to this carbon, but it is far away. Hence you get 3 signals, B, C, D. Okay, and this methyl group also, here also there is a carbon, right? So you will get 4 signals. Okay, 4 signals for this compound, right? Now see here in this case, see these are all very simple, right? These are all very simple. You can just draw a plane of symmetry, and by the plane of symmetry you can easily predict the number of signals. Okay, see in this case pyridine, after after bisecting the pyridine, what will you get? Here there will be a carbon, here there will be a carbon, and here there is a carbon. Okay, so you will get 3 signals, right? You will get 3 signals because this nitrogen is ortho position. This carbon is in ortho position to that of the nitrogen, but this carbon is in meta position with the nitrogen, and this carbon is in para position with the nitrogen. Hence these carbons are different. It will have 3 signals. Okay, similarly in this case also, see here, this is a carbon and this is also carbon. Okay, this carbon is attached to the sulfur, whereas this carbon is attached to the carbon that is attached to the sulfur. Here you will get 2 signals. Okay, 2 signals. Similarly here also you will get 2 signals, right? This is how you have to solve these questions. And these are all heterocyclic compounds, right? I have told you in aromaticity. Can you predict the aromaticity order here? See, whenever you are studying some concept, try to correlate with the other concepts that you have studied already. Okay. Now I have given these compounds, but after seeing these compounds, you have to remember that these are all heterocyclic compounds and these are all aromatic in nature. So can you predict the aromaticity order? These are all 5-membered, these are all 6-membered. I told you in the aromaticity topic that there is a trick. 6-membered ring will be more aromatic compared with 5-membered ring, right? So if you know that trick, you can directly find out that pyridine will have more aromatic nature. Okay, and after that, see here, nitrogen, sulfur, both are 5-membered ring. Now how will you identify which will have more aromatic nature? It is very simple. I told you that aromaticity is inversely proportional to electronegativity. Aromaticity is inversely proportional to electronegativity. Okay, so if aromaticity is inversely proportional to electronegativity, here nitrogen or sulfur, which is more electronegative in nature? It is nitrogen, right? Nitrogen is more electronegative in nature and aromaticity is inversely proportional. Hence, sulfur will have more aromatic nature, okay, than that of the nitrogen. Why? Because if it is more electronegative in nature, it will try to pull the lone pair of electrons towards itself. This lone pair of electrons will not involve in conjugation. If it doesn't involve in conjugation, definitely it will be least aromatic, right? Comparatively, sulfur is less electronegative. It won't pull the electrons towards itself that much when compared with nitrogen. Hence, this lone pair of electrons can involve in conjugation. As a result, it is involving in conjugation. It is aromatic in nature. Okay. So, this is the order. Pyridine will have more aromaticity, and then thiophene, and then pyrrole. Okay, pyrrole. Right? This is the order. Now, can you predict the number of signals for benzene, naphthalene, and anthracene? These are all very simple, right? Already we have found out the number of signals in proton NMR also, right? So now we are going to predict the number of signals in C-13 NMR. See, for C-13 also, these 6 carbons are on same environment, right? See here, this carbon will have hydrogen. This also will have hydrogen, hydrogen, hydrogen. See, this carbon is attached to a carbon having hydrogen. This carbon is also attached to a carbon having hydrogen. All these are in same environment. Hence, it will have only one signal. Okay, only one signal. Right? Now, in case of naphthalene, see, these 2 carbons are different, right? These 2 carbons are different. These are all present in the inside the ring. Okay, inside the ring. These are all peripheral. Okay, these are all peripheral. And this is different. These two are also different. So, if you have plane of symmetry, first draw a vertical plane. Now you can draw a horizontal plane. Now look at the number of carbons. See here, 1, 2, 3, right? You have 3 carbons. It is very simple. See here. This is naphthalene, right? Naphthalene, you can draw plane of symmetry. How will you draw the plane of symmetry? Vertical plane is here, right? And a horizontal plane is also here. So, after you have drawn the plane of symmetry, just look at only one side. How many number of carbons are there? Here there is a carbon, here there is a carbon, and here also there is a carbon. So, 3 signals, okay? So, naphthalene will have 3 signals. Now we are going to predict the number of signals for androgen. Okay. In this case also, you can draw a vertical plane because it can bisect, and similarly you can draw a horizontal plane because it can bisect. So now count the number of carbon atoms. See, this is carbon 1, 2, 3, 4. Okay. You have 4 different types of carbons. Hence, it is having 4 signals. Okay, 4 signals. This is how you have to predict the number of signals in C-13. It is similar to that of the proton NMR only. Okay, I hope this is easier for you guys. Okay, now we are going to predict the multiplicity. Okay, we are going to find out the multiplicity for this. Okay, carbon 13 multiplicity. Generally, what is multiplicity? You will find out that in n plus 1 rule, right? Because the neighboring proton, in proton NMR, you will look for the neighboring number of protons, right? See, for example, in this case, if you want to find out the multiplicity in proton NMR, what will you do? Suppose I want to find out the multiplicity of this compound. I mean, for this hydrogen, you will look for the neighboring proton. There is only one proton, okay? Here there is no proton, only one proton. So, n plus 1, 1 plus 1, it is 2, doublet, okay? This is doublet, right? This is how you will find out in proton NMR. But here, in this case, it is quite different and also very easy, okay? Quite different and also very easy. Because this carbon 13, like this carbon 13 nucleus is a dilute nuclei, okay? The abundance is very low. Natural abundance of this carbon 13 is very low because naturally available carbon isotope is 12 carbon, okay? You would have studied that there are 3 isotopes of carbon, 12 carbon, 13 carbon and 14 carbon, okay? Carbon 13, carbon 12, carbon 14 are possible, okay? So, in carbon 14 is radioactive nuclei, okay? Carbon 14 is radioactive nuclei. Carbon 13 is very much lower in abundance. It will be around 1.1%, okay? 1.1%. And carbon 12 is the natural element. It will be around 98.9%, okay? 98.9%. So, see here, this is very rare, okay? Carbon 13 is very rare. 1.1% only, dilute nuclei. So, it won't couple with the neighboring proton, okay? It won't couple with the neighboring proton. So, if you want to find out the multiplicity of C-13, it is very simple. Just look for the number of hydrogens attached to the carbon. See, in this case, if you want to find out the multiplicity, 3 hydrogens are attached to carbon, right? Hence, this is quartet. Okay, this is quartet. This case, this carbon is attached with a hydrogen. You need not look for the neighboring carbon and all, okay? Just number of hydrogens that is attached to the carbon. It is 1, right? Hence, this will be doublet, okay? Doublet. See here, in this case, only 1 hydrogen is attached to carbon. Hence, this is also doublet, okay? Here, there is no hydrogen attached to it. Hence, it is singlet, right? Now, in this case, the carbon, 3 hydrogens are there. So, this is also quartet, okay? Quartet. This is how you have to find out the multiplicity in C-13 NMR, right? Here, I want to know the multiplicity of this carbon, okay? This carbon attached to a chlorine, hydrogen, these and all, okay? I want to know the multiplicity of this carbon. You just comment it in the comment section. Okay? What will be the multiplicity for that carbon? So in this video we have seen about a basic intro about C-13, okay, its natural abundance and the comparison of various isotopes of carbon. And then we have seen the chemical shift values. If you know the chemical shift values, you can easily predict the structure, okay. You can elucidate the structure. Next we have find out the number of signals for few compounds. And then I told you how to calculate multiplicity in case of C-13, okay. It is quite different from that of the proton NMR, but it is very simple here, right? It is very simple to find out the multiplicity. If you find this video helpful, then kindly subscribe and share with your friends. Stay tuned. Thank you so much for watching.